Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back again to this online NPTEL structural geology course. We have delivered so far almost 7-8 lectures including lab part to measure deep and strike. I hope you're enjoying these lectures and it is not too difficult to follow. I repeat again, if you have any issues with any of these lectures or any of these points or slides, you are most welcome to write back to us, to the two teaching assistants or directly to me to get clarifications of your questions or whatever confusions you have about this subject. Today we will cover a new topic very much related to the topics we covered before, strain, and this lecture will cover stress. And I must say that in structural geology, stress is one of the very important components or pillars. Without understanding of this particular topic, stress, it is extremely difficult to understand or to comprehend the structures that we see in the field. This subject stress includes concept of mechanics, forces and stress, their dimensions, their units. Then we will slowly move to some sort of very basic mathematical operations to understand what is the stress on a surface, what is the stress at a point, and then we slowly move to a concept that is called stress tensor. After that we will look at stress ellipse and stress ellipsoids, and we will conclude this lecture with the concept of compressive, tensile and shear stresses. We will also look at what are positive stresses and what are negative stresses that we consider in particularly structural geology, and how do these concepts that we particularly apply in structural geology do vary from other subjects. Now, it is very important to feel that stress is something that we do not see, but we feel its effect. In the context of geology, or to be very specific structural geology, we are convinced now, so far the lectures we have, that rocks do get strained, and if you have strain in your rock that you are considering with, that means it must have moved from its original place, and at the same time it also has changed its shape and dimensions, that means it got distorted. Now, to achieve this strain in these rock masses, who does it, or who is the driving mechanism responsible for this strain in the rock? And the answer is that this strained material, when it was getting strained, it must have experienced some sort of natural forces or pressures, or it was subjected to some sort of natural forces and pressures. And I repeat that we do not see these pressures or forces, but we feel it, and this is what we would like to continue in these lectures. But before that, let us have some basic ideas of this general topic overall. Now, first of all, you must have heard this word stress from your school life. You must also have heard this word force again from your high school levels, and we know that the forces or stresses, whatever we consider, these two things, they have to act on some materials. Now, rocks, as we can figure out, that is essentially some sort of materials, a special kind of materials you can think of. But so the study of deformation of rocks under forces certainly falls under the subject mechanics. Now, mechanics is something that is a topic, is sort of a topic that we cover in physics mostly, that deals the science related to the behavior of physical materials. That means that you can visualize, you can feel, you can touch it, subject it to force and displacements. So, therefore, if we consider rocks as our materials, then we have learned that these materials, rock materials, do get strained because of some sort of forces and pressures. And if so, then we can study the effect of forces and pressures on the rock materials to achieve some sort of strain. We can study it under the broader umbrella of the subject mechanics, and we generally call it, I am sure you have heard this term, rock mechanics. So, it is very interesting that we will see how rocks as well, like all other materials, we can study under the subject of mechanics, and at the same time we will look at that there are many branches of mechanics. So, you must have heard quantum mechanics, you must have had continuum mechanics, solid state physics is also a type of mechanics that people do study, and we will see that in rock deformation or in structural geology we will consider a particular type of mechanics, and this is known as continuum mechanics. So, before that let's get the idea that what is a continua, or what you consider continuous in the context of structural geology or in the context of general behavior of materials. As it is written in this slide, that a body is and remains continuous under the action of external forces. We will learn very soon what is force. So, it must have some sort of criteria that only we learned what is continuous and discontinuous, and the same concept more or less I can apply here as well. So, it says that consisting of continuous material points. That means, if you consider a material that should not have any voids in your scale of observations. So, it should have continuous materials. It can be different materials, but it has to be very much continuous, and we can see that for rocks, or we can feel that for rocks this is true, it holds good. And before and after the deformation, the neighboring points remain neighbors. That is one of the primary considerations of a continuous deformation. Now, this may not hold true for the rock deformation. We have seen a number of examples of discontinuity in rock deformation. Some structures we have seen where the continuity do not remain. Let us keep this in question. And it does neglect all sorts of atomic structures. That means, it does not go to the very detailed atomic scales features. So, if we consider these three, and of course, in the rock mass looking at its scale, though we do nowadays study a very detailed microstructures, even we go to nanoscales, but we hardly, except a few cases, few very specialized cases, we deal with atomic structures and their distributions for studying deformation of rocks. But in general, we can figure out that if these three conditions hold good for any material, and we are studying its deformation under the action of forces, then we call that it falls under the subject of continuum mechanics. So, therefore, a continuum or continuous medium, you can consider as it is written here, is represented as a continuous aggregates of idealized material particles. That means, it must have some sort of elemental volumes. Now, these elemental volumes, they are small enough that their position can be given in terms of points in a set of coordinate systems, whatever coordinate you can consider, but it is large enough that local value of any variable does not depend on fluctuations at the atomic scale in the immediate neighborhood of the point. So, this subject is being studied under a sweet spot, that it is not that small that you cannot plot it in a coordinate system, but at the same time it is not that big that some small fluctuations at the atomic scales can affect your system. Now again this is a little confusing for studying the earth, because earth is really big, and a little fluctuation somewhere can cause large fluctuations in other places. So again there are some sort of approximations, and what is most important, that when you model something or when you study something, you actually ignore some very micro scale features. What I try to say here, that if you are studying a grain or grain scale processes, then you do not take care probably what is happening at the top of the mountain, or you do not care if there is a lot of deglaciation or there is a huge rainfall. These things probably do not affect your scale of study. Now if you go to little larger scales, for example if you are studying a rock specimen, then you do not take care of these internal features inside a grain, for example dislocations or some crystal vacancies or some interstitial impurities inside the crystals. When you study a rock specimen, you do not consider all these little things, you ignore them, you believe that these things do not affect this. If you are studying a scale of plate tectonics, then you do not consider the different layers that we see in rock systems. For example, you do not consider a shale layer or sandstone layers and then limestone layers and so on. These things we ignore when you study the scale of plate tectonics. Now if you consider the scale of geodynamics, then we consider crust, mantle and core. We hardly consider the fact that crust has different layers, mantle has 2 different layers, or maybe we consider, but the scale increases. We do not really consider that whether in the crust we have carbonates or we have silicates, or whether in silicates we have shale layer somewhere or sandstone layer somewhere. These things do not influence the research of your study. If you would like to study the solar system entirely, then you consider all the planets just as a sphere, right. So there you do not consider what is your core, what is your mantle, what is your crust and so on. So the bottom line is, based on the scale you are observing, so scale term is very important, as I said in the first lecture. Based on the scale you are observing, or your area or your interest, you somehow approximate some features and you somehow neglect some features by approximating that these features which do not really fit to your scale carrying out or can influence your measurements or your analysis. So this is the concept of continuum mechanics, and we will see that stress and most and strain as well that we have learned, these are being studied, and the next after few lectures we will study rheology. These are subjects which are being studied under the broad umbrella of continuum mechanics. So I hope I can send you the message of why we should, or what is the justification of studying stress, strain and rheology like subjects, particularly important for structural geology under the umbrella of continuum mechanics. There is also one important point, that the approximations, the assumptions, the equations, everything in continuum mechanics is little simpler compared to other topics, and it is easy to understand, easy to employ, easy to apply in the problems that we generally face in structural geology and tectonics in general. So we move on, and we first get the very basic idea of what is force. Now if I ask you what is force, then generally the common answer we get that force is a pull or push of a body, or that you apply to a body. So you are pulling a body, that means there is a force, you are pushing a body, that means there is a force. Now this is true, but this is not absolutely true in defining the force. For example, I am standing here, apparently no one is pulling me or no one is pushing me, but there are some forces, there is at least one force acting on me. So that is the gravitational force which is going down, and then there is an opposite and equal force which is acting from the ground to me, and that is why I am more or less balanced here. So it is the interaction of the material to some quantities. So we can define that an object in motion or in equilibrium is a function of the object's mechanical interaction with the other objects. Now, force is the quantitative measure and description of this particular mechanical interaction. So, that means if you have a material, then how this material is interacting with its neighboring or other objects is the study of force, or it is defined as force if you can measure it quantitatively. And that means not necessarily all the bodies have to be in motion to identify or to measure force. Now, force we know from high school level is a vector quantity, that means it is a first order tensor. Now, this is something, a new term maybe you are hearing. We will not go into the very detail of what is tensor, but any scalar quantity we call it zeroth order tensor. That means it has 0 order, that means it has only magnitude, no directions, nothing. So, it is 0th order tensor. Vectors, it has magnitude and directions. So, therefore, it is first order tensor, and there are possibilities of some second and third order tensors, and these are not typically vectors or even higher order tensors. We will learn about it soon, but not in detail, but we will just describe what is this. So, a vector is generally first order tensor. Let us get into that only. So, force, as it is a vector quantity, it has a magnitude and direction and point of application. The SI unit of force, you know, it is Newton. 1 Newton is required to accelerate 1 kilogram mass at 1 meter per second square. And if we see its dimensions, then it is m L prime 1 and T prime 2. That means mass, length and T. So, this is how m, L, T are considered. So, would vary when we consider other materials. Then there is also one unit of force that people commonly use is called dyne. So, 1 dyne is required to accelerate 1 gram mass at 1 centimeter per second square. Now, to get the concept of Newton, or just to see that what is 1 Newton, you can actually do it very simply. I just tell you that it is about 102 grams weight. If you keep it and leave it on the earth's surface, then you are generating actually 1 Newton force on the earth's surface. So, you just have acceleration of gravity of earth, and then you add it to this weight, and then you would figure it out that it would come to almost 102 grams. Now, because force is vector, so you can represent it through a coordinate system in 2 dimension and 4th dimension and 3 dimensions, I am sorry. So, what you see here in this illustration, so this is a force, a point which is say being applied to this direction, to the center of this coordinate system x1, x2 and x3, and we can resolve this force vector in 3 different components acting parallel to x1, x2 and x3. And if we assign it fx1, which is acting parallel to x1 direction, then it is f cos alpha, where alpha is the angle between the force vector and the x1 axis. And similarly, you can have fx2, where you can represent by f cos beta, where beta is the angle between the force vector and the x2 axis of this coordinate system, and fx3, where f cos gamma, where gamma is the angle between the vector f and the axis x3 of this Cartesian coordinate system. And because these are related to each other with this equation, that means a square of this force vector would be sum of the squares of fx1, fx2 and fx3. This relationship holds good, you know it from your high school level. Now, there are classifications of forces, there are different classifications, but in general forces when it act on a body, we can basically divide into groups. One group is internal forces and another group is external forces. Now, internal forces is something that you can define it, that it represents the interaction between the particles in the body. So, triatomic forces, interatomic forces, inter or intermolecular forces, these are generally considered as internal forces. External forces on the other hand, that is something when you have interactions of your concerned material on the particles of other particles of the given body, or what I mean by that, it refers to the action of other bodies on the particles of a given body. That means it has to come some sort of externally, and this is something we generally consider. And external forces are also classified in two different ways, or in two different subsets. One set is body force and another set is surface force. Now, body force is when it acts on unit mass or unit volume of the body. And in the context of geology or structural geology, in particular, gravity or gravitational force is the force that you can consider as body forces. Then there could be the magnetic forces that also are a type of body force. Now, surface force, that is something very important to us, is defined as is the surface forces do act on the surface of a body when it comes in contact with another body. The surface forces are mostly responsible for the deformation of rocks at various scales. So, you need a contact to have some sort of surface forces, otherwise your body will not deform, and if there is no distortion, no deformation, then you are not dealing with surface forces, you probably are dealing with body forces or some other forces. Now, surface forces, because it has to act on an area of the object you are considering with, so this is often referred as traction. So, we will see what traction is, that when a force acting on an area, sometimes we call it traction. You remember this term, we will use it soon. So, let us have a look first on the stress term when it is acting on a surface, or we define it as traction. The stress on a surface can be idealized in geological context in many different ways. For example, when you have a fault plane, then two planes are moving past each other, keeping a contact, or you can imagine that two grains are in contact in a very micro scale, and one grain is transferring its stress to the neighboring grain. That means it is generating a traction at the grain boundary. You can consider of meteoritic impacts and so on. These are some very visual examples, but wherever there is a deformation, there is a traction. You can think this way. So, the definition of stress, generally we say, or we commonly say that what is stress? Force per unit area. You are right, but that is not absolutely true. It is actually the reactive force per unit area. That means, if I apply a force here, and if I calculate, if I know the magnitude of this force that I am pushing my left palm with this right hand punch, then if I take this force and divide it by the area of my left palm, I will certainly get a value, but that is not stress. Stress is I am applying this force and my left palm is working or pushing with an opposite and negative force to the force is being applied by my right hand, and this force is reactive force. It acts following the Newton's third law, and this force divided by the surface area is the stress generally defined. So, the stress on a surface, or you can say traction, we will define it as T, as defined as the ratio between the reactive force F and the surface area S on which the force is acting. So, therefore, we define that this is what is your reactive force, it is a vector force, then this is the area you would like to work with. So, this T is the stress or the traction. Now, because force is a vector, so the stress on a surface or traction must be a vector as well. Now, because we are adding some area or dividing the Newton by area, then unit of stress should be Newton per meter square. Okay. Now, this Newton per meter square has a name, and this name is Pascal, and sometimes it is written as PA, capital PA. Now, 1 Newton per meter square is generally, you can sort of expand it. So, it is 1 kilogram per meter per square, and the dimension here changes to ml power minus 1 t power minus 2. Now, there are many other units of stress. Sometimes we also call it pressure in the context. So, 1 Pascal is equivalent to 10 to the power 5 bars. Now, this 10 to the power 5 bars, that means 5 zeros after 1, and this is about 0.000145 psi, pound per square inch, and 1 megapascal, therefore 1 into 10 to the power 6 Pascal is equivalent to 10 bars and 145 psi. Now, what is 1 Pascal or what is 1 megapascal, how much it is? I give you an idea, or it is written here, you can read. The normal bicycle that we ride every day, the tire of these bicycles have some pressure, so you have to pump it. So, the general range is mostly 0.5 to 0.7 MPa in a normal bicycle tire. In a car tire, it goes to 0.24 megapascal or 0.3 megapascal maximum, but that is in a very rare case. So, the pressure on the bicycle tire is 0.6 megapascal, and the lithostatic pressure at the lower upper mantle boundary, which is around 670 kilometers down from the surface, is about 25 gigapascal. That means 1 MPa multiplied by 10 to the power 6 multiplied by 25 gives you the gigapascal. At core mantle boundary, it is about 330 gigapascal, and at the center of the earth it goes close to 400 gigapascal, where the temperature is close to 6000 or 7000 degrees centigrades. So, this is the range of pressure, or this is the magnitude of the pressures that structural geology, tectonics or geodynamic people think and work with, right. So, we will look at now that how to mathematically describe the stress on the surface element, but before that we will take a break. We will continue this lecture in the next segment. Welcome back. So, in the previous segment, what we learned, that what is stress on a surface, what is its dimension, what are the units, and more or less we have an idea that what is mean by stress on a surface. Now, in this segment we will learn mathematically how to express what is stress on a surface, and for that we will consider some sort of approximations under the broader umbrella of continuum mechanics. So, stress on a surface element, to consider that, let us consider a continuous medium which is occupying a volume V, which is this larger area that you see, this one. Okay. So, this is volume V in Cartesian space, and within this you have a very little element, volume element, which is delta V inscribed in the volume V. Now, if we consider this volume V, now why I am considering this? I am considering this entire V is a very large body and it is a continua, and within this continua I am considering a very small volume. Okay. Now, if I consider this very small volume del V, then as we have learned, the two different forces would apply on this. One is body force, which is acceleration of gravity, which is x I, and then surface forces that must act on a very small surface. So, let us consider that this is del S, which is this entire area. On the surface of this volume, a force is acting. Okay. Now, we can consider that this a very small surface within this volume del V, which is del S, and on this del S, this force which is acting, say some sort of F or whatever, or del F I. Now, what is this I here? Like as we said, this Ni is the unit normal vectors. So, if I consider any surface or any plane, then it must have 3 unit normal vectors parallel to the coordinate axis, right. So, if I have this very small area, and then this del F I is the surface force acting on that very small area del S of this body, then this little green this little blue surface area would react to this force del F I, right. So, it would exert an equivalent and opposite force, and it would produce a couple. Now, I repeat that I have a large volume V. Within this large volume, I have a small volume which is delta V, which has a surface area delta S, and within this small volume, small area delta S, we have a very small area del S, where a force is acting, and because a force is acting on that little surface, it would exert an equivalent and opposite force and produce a couple on the surface del S from inside. So, now if we consider del S tends to be 0, that means it is a very, very small area, then the couple vanishes, and the ratio, that means del F I and del S, tends to be a finite limit and can be defined by a vector which is traction. Now, by doing this, that means I have a very small area, I am applying a force. So, we are getting an opposite force on this same point from the other side, and this is del S, this is del F I. So, if this area goes very small, so therefore, I have an area which is del S, and I have a force acting on this del F I, and if I reduce this area, that means the area tends to 0, then I get some sort of in a very small area the stress or the traction on a surface. So, mathematically we can define it this way. Even if you not consider this strange mathematical notations n and I. So, traction is equal to the limit where del S tends to 0 is f del F I divided by del S. So, this is the mathematical expression of stress on a surface area. Now, this is not really very straightforward expression as force per unit area or reactive force per unit area. So, in stress, in considering stress, this is how we apply the definition of stress on a surface element. Now, we clearly see that if we have a surface and I have a force acting on this surface, say this is how it is working. Now, because this is a vector, we have understood before that traction is a vector. I can resolve this vector one way, that is perpendicular to this plane, and another way parallel to the plane. the force vector or the component of this force which is perpendicular to the plane is known as normal stress vector, or we define it or mathematically write as sigma, that acts normal to the surface, and there is a force that acts parallel to force component we can resolve that acts parallel to the surface, and this is known as shear stress vector, or mathematically generally written as tau, which acts parallel or along the surface. Now, in most of the geological cases, the stress vectors in general act obliquely to the planes. So, a structural geologist have to decompose these stresses, I repeat again. A structural geologist therefore has to decompose the stress vector to normal and shear stress components with respect to the orientation of the concerned surface. Now, we will learn about this technique later, but what I tried to convey with this statement, that if we have a force acting on this surface, we can immediately resolve it to the normal and stress component by simple vectors. But for stress or for traction, it is not that straightforward, because you have to also consider the orientation, the area and its orientation where the traction is working with. Now, once we have more or less a steady idea that what is stress at a point, now we would like to see stress on a surface, I am sorry, and then we would like to switch to another part, and which is even more relevant, that is stress at a point. So, let us talk first about the concept. As I said, in structural geology we often consider stress at a point. For example, a point inside a crystal or mineral, or a very tiny inclusion within a grain, and we would like to know what is the stress acting or what is the stresses in this point. Now, we will follow the same process. So, we have the same drawing again, we have this volume V somewhere outside, and I just highlighted the area here where you have del V, then you have delta V, delta S, and then del S, a small surface, and we have again the same point P, along which or on which we have already derived, we have generated a very small surface, and we looked at how we can get the stress on a surface resolved. Now, to get the stress at this particular point, if we consider a point is now inscribed in the volume del V, and if I consider this as a point P, then it is possible actually I can draw infinite number of surfaces around it. What I mean by this, if I have this point P, then I can draw infinite number of surfaces and so on. And these surfaces are very small because these are around a point, and on each surface we can calculate what is the stress, because stress classically is defined as reactive force per unit area. So, in short, that you can imagine an infinite number of very small planes around the point and resolve the tractions on these small planes and define the stress at a point. Now, this is some sort of approximation or consideration, and these areas have to be very, very small. Now, on each pair of opposite planes around the point, we can resolve two perpendicular and oppositely directed with equal magnitude, therefore equal length component of the stress vectors. We will learn about it very soon. Now, if I have a little point here and I have two planes oppositely directed, I have two planes oppositely directed, I have two planes oppositely directed, and so on, and a force is acting on this plane, then it is highly possible that this oppositely directed magnitudes are equal, but with other pair of oppositely directed planes the magnitude may be different. That means, if I have a point here, I have two surfaces it may be acting like this, and I have 2 points here, the magnitude. In these two cases, here and here the magnitudes are same, but their magnitudes are different in the other two pairs. So, if I consider many such planes, and these magnitudes may vary constantly, and this would come, or this would finally yield what we would call very soon as stress ellipse when we consider it at 2D, and what we would call stress ellipsoid when we consider in 3 dimension. But before that, let us again come back to this particular topic, stress at a point. Now, what we can do actually, we can draw a very small unit cube around this point P, considering 6 of these many surfaces that is possible to draw around this little point. Now, these 6 surfaces, one pair of each, are aligned perpendicular to one of the principal axis of stresses. So, how it would look like? It would look like something like this, what we are seeing here. We have these reference frames in Cartesian coordinates x1, x2, sorry x2, and here is x3. This blue dot here is the point P, and we have considered 6 planes. In the positive side, we are seeing now 3 planes, there are of course the 3 planes on the other side. So, this plane where I am marking a little dot is perpendicular to your x3, this plane is perpendicular to your x2, and this plane is perpendicular to your x, and these 3 planes and their opposite planes hold this point P. So, this is a very magnified view of around a point P. Now, we know that a force is acting. Now, we know that a force is acting here, and for each surface we have defined following attraction that there should be a normal stress and there should be a shear stress. Now, normal stress, for the normal stress, if we consider this plane which is perpendicular to the x1, the normal stress on this plane which is perpendicular to x1 certainly would be directed along the x1 direction, which in this case is sigma 1 1. Now, the shear stress, again we can resolve it in 2 different components, because one would go along the x2 direction and one would go towards the x3 direction. So, we actually get 3 mutually perpendicular set of stress components, one of them which is a normal stress component and 2 of them are the shear stress component, and one of these 2 is aligned to x2 and this one is aligned to x3. And a similar case happen if we consider the plane which is perpendicular to x3, that means sigma 3 3 is a normal stress component working along the direction of sigma 3 3, then 2 shear stress component tau 3 2 and then tau 3 1. And then similarly on this plane which is perpendicular to x2 direction, we would have normal stress component which is acting towards x2 and then 2 shear stress components. Now, you have seen that 3 different nomenclatures or different notations are given. Let me explain what it is. What we see on this plane, I come back again to this plane. So, sigma 1 1, tau 1 2 and tau 1 3. In this case, this first index in each of these stress components indicate the plane it is acting or the plane perpendicularly it is acting. So, in this case this plane is perpendicular to x1. So, therefore, in all cases this is first component is 1. That means, these sigma, this tau and this tau, these stresses are working on a plane which is perpendicular to x1 direction. The second component 1, 2 and 3 are the direction along which the stresses are working. So, in this case the second component here is 1. So, it is working along the x1 direction, tau 1 2 second component is 2. So, this is working along the x2 direction, and this is 3 tau 1 3 is the last component. So, it is working along the x3 direction, and this is also obvious or applicable for the other two planes. The other three negative planes that we do not see in this image and exactly oppositely directed, and but similar magnitude stresses would work there. So, if we now come back to our traction idea or what we have learned from the traction. So, on each surface we have, in this case this is parallel to, or sorry, perpendicular to x1. So, here I can here I can write that this is T1, that means traction working on the plane which is perpendicular to x1, traction working to perpendicular to x3 which is T3, and this one is T2. Now, for each of these T1, T2 and T3, we see that we have three components to define the stress on this plane which is perpendicular to x2. But everything we are doing to define the stress along this point P. So, to define the state of stress along this point P, we first have to resolve the stresses acting along the three surfaces. So, for T1 we see that this is sigma 1 1, tau 1 2 and tau 1 3 for the face normal to x1, tau 2 1, tau 2 2 and tau 3 3 for the face of normal to x2 which is tau 2 for traction 2, and then traction 3 is tau 3 1, tau I am sorry, this must be tau 3 1, tau 3 2 and sigma 3 3 which is normal to x3. Now, all these 9 components that we see here are required to define the stress at this point P, and each of them, as we have understood, these T1, T2 and T3, these are tractions and tractions are vector. But when we need all these 9 components, 1, 2, 3, 4, 5, 6, 7, 8, 9 components to define the stress at a point, it does not remain a vector anymore. It comes to a new component or new sort of dimensions or description of the parameters, and this is known as tensor. So, you can write these 3 components in a matrix form: sigma 1 1, tau 1 2, tau 1 3, tau 2 1, sigma 2 2, tau 2 3, tau 3 1, tau 3 2 and sigma 3 3, and you can simply notify or note it in the form of index notation sigma ij, and this is your stress tensor, which is neither a scalar quantity nor a vector quantity, but a tensor, and I tell you this is a second rank tensor. So, force or traction was a first order tensor and stress at a point is a second order tensor, and this is neither a vector nor a scalar. So, I believe you have now the idea that from the traction which was a vector, now we arrived to a new concept. When we have to define the stress at a point, it cannot be a vector, it is a tensor, and in 3 dimension you need 9 components, and in 2 dimension you can define it only with 4 components, but it would still remain a tensor. Now, there are some fundamental equations that we need to know or learn, and which is known as equilibrium concepts of stress tensor. I am not deriving these equations, but as I have noted here, you can get this from the book, one of the books I referred, Professor S. K. Ghosh's book. If you go to chapter 5, you can see what is this. But the concept of this equilibrium or stress equilibrium is that this cube would stay in a static mode. That means it does not translate along x1, x2 or x3 direction, or it does not rotate. So, if it has to translate, then we have to consider the body and surface forces. That means body and surface forces, the sum of body and surface forces in a particular direction should be 0. That means they are balanced. So, this is for x1 direction, this is for x2 direction, this is for x3 direction. You can get these three equations, and in index notation form you can write it this way. And if that this is not rotating, that means it is not rotating this way, say for example clockwise. Therefore, this tau 3 2 has to be counterbalanced by on the other side tau 2 3. And we can show that in an equilibrium condition this is possible. That is the only condition that it does not rotate. So, this is the equilibrium that we consider for moments, and therefore, it defines, as I said, tau 3 2 has to be equal to tau 2 3. Therefore, sigma ij should be equal to sigma ji when your body is in equilibrium. And therefore, here we had sigma ji, you can simply represent sigma ji to sigma ij. I did not dedicate too much time on this, because you can get these derivations from other books, but I hope you have now understood the concept of stress on a surface, which is a vector traction, and stress at a point, which is a tensor. Now, let us come back to the concept of stress ellipse and stress ellipsoid. As I said that on this particular point P here, we can consider n number of planes surrounding this point P, and oppositely oriented planes would have same magnitude, that means same length, but different directions, different senses of action. So, if we look at this is the point P here, and if we look at in 2 dimension, then we may get actually. So, these are actually, for example, if I consider these 2 red arrows. So, around this we had this plane and this plane, around the small arrows, small red arrow, we had this plane. So, here it is working on this side, here it is working in this side, their lengths are equal, that means magnitudes are equal, but their orientations or action directions are different, and similarly here. Now, of course, you can have n number of planes around it, and you can draw their normal components with their respective magnitudes. So, if you connect all these points, you certainly would get or end up with an ellipse, and this ellipse is known as stress ellipse when you consider in 2 dimension. The maximum length you get, we will define it as sigma 1, and the minimum length we get of this stress magnitude, we define it as sigma 3. In 3 dimension, very similar to the strain ellipsoids, we look at, we would get a very similar shape. So, at the maximum we would get sigma 1, at the minimum we get sigma 3, and intermediate we get sigma 2. Now, what is sigma 1, sigma 2 and sigma 3, and how does it differ from this sigma 1 1 or sigma 3 3 or sigma 2 2? We will hear it in the next lecture, we will learn it on this next lecture. But before that, let us get some more ideas about the stress ellipsoid. So, the geometric disposition of the stress ellipsoid, its shape and orientation is generally described by the stress ellipsoid, and it reveals the state of the stress at a given point in a rock mass deforming, or if it is even in a static mode. Now, this is something very important that we have just learned. Not necessarily you have to deform a material that there is a stress, or because there is a stress, not necessarily the rock mass has to deform. And we have just learned that the largest, smallest and intermediate axis, which will define sigma 1, sigma 3 and sigma 2 respectively, of the stress ellipsoids, this one and this one, are known as principal stress or principal axis of stresses of the stress ellipsoid. This is something which is very interesting. We will again learn about it later in the next lecture. But let us have some very basic ideas that the stress and strain ellipsoids, they look very similar. I just changed the colors, but they look very similar. Their physical appearances are very similar, their mathematical descriptions are also very similar. However, always remember that these are different. A stress ellipsoid may not lead to a strain ellipsoid, that I just said that rocks are not deforming. And importantly, the shape and the orientation of the strain ellipsoid may be very different to those of a stress ellipsoid responsible for the strain. And now we would see that what are compressive stresses, tensile stresses, shear stresses, and what are their sign conventions. Now, compressive stress is the stress on rock mass which tend to shrink or shorten the material along the direction of applications. And if you have a domain of compressive stress, you form structures like folds, buckle folds or thrust faults. So, for example, if I have a layer embedded in a body, embedded in a matrix, and if I apply the stresses directing towards each other, I will produce a fold, and it is a compressive stress. If there is tension on the same layer, then I may produce a structure which we call budinage, we will learn about it soon, then stress is tensile stress. In structural geology, interestingly, we consider compressive stress as positive and tensile stress as negative. If you read literature of any other engineering subjects or physics like mechanical engineering, material science, you will see their conventions are exactly opposite. Compressive stress is negative and tensile stress is positive, and this is because we will learn later that tensile strength of any material is less than its compressive strength. And because material scientists or mechanical engineers, they every day use or their applications are mostly with the practical materials, so therefore they are most concerned with the tensile stress. And in earth, most of the stresses are mostly compressive, so we deal mostly with compressive stresses. So mostly to deal with some sort of mathematical easiness, we use compressive stress as positive and tensile stress as negative. Now, shear stress is the stress on the rock mass we have learnt that acts along or parallel to the surface. That means you can consider the stress along the fault plane. In this case, if I have shear stress working like this on this elliptical object, and the rotation of this elliptical object due to application of the shear stress is anticlockwise, then we consider it positive. If not, that means if it rotates clockwise, then we call it negative. Though we do not call it positive or negative way, generally in structural geology we call this type of, that means when top part goes towards your left side, we call it sinistral, and this one we call it dextral. We will learn about it soon. So, with this note I conclude this lecture, and in this lecture we have learnt the basics of force, stress on a surface and stress at a point. We also learnt that why stress on a surface is vector, and stress at a point is a tensor. This is something confusing, but this is how it is. And we also learned what are principal axes of stresses, but we will learn about it soon. So, this is the topic of the next lecture. We will focus upon the characteristics of the principal axis of stresses, how they are derived, what are different mathematical considerations are involved, their different components, and we will also look at in detail the shear stress components. Thank you very much. See you in the next lecture.